So, to start talking about binomial distributions, we first have to talk about Bernoulli trials. A Bernoulli trial is an experiment with exactly two outcomes, a success and a failure. So, flipping a coin can be heads or tails. Picking a card from a deck, we could say a black card or a red card, or face card or not a face card, or heart or not a heart. The Earth gets hit by a meteor. Either it does or it doesn't. The probability of success and failure do not need to be equal. There just has to be only two outcomes. And usually, for most events, we can make it be only two outcomes depending on how we phrase things. So, like, rolling a die has 6 outcomes. But if I say getting an even number on a die versus getting an odd number, or getting a 1 versus not getting a 1, then I have changed that to be 2 outcomes, and then I can use, then that is a Bernoulli trial. And this is important because a series of Bernoulli trials form a binomial distribution. So, for example here, we're going to talk about the Milgram experiment. If you took AP Psych, you probably remember this, because it's kind of messed up. Stanley Milgram was a Yale University psychologist, and he conducted a series of experiments on obedience to authority starting in 1963. They had an experimenter who ordered a teacher, who was the volunteer subject of the experiment, to give severe electric shocks to a learner each time the learner answered a question incorrectly. The learner was actually an actor, and the electric shocks weren't real, but a pre-recorded sound would play every time the teacher administered a shock that sounded like a shock, and the actor would pretend to be in pain. And so they were measuring the willingness of study participants to obey an authority figure who instructed them to perform acts that conflicted with their personal conscience. So, what percentage of people were willing to continue to administer painful electric shocks to another person because someone in a lab coat told them to? And about 65% of people would obey authority and give such shocks. Over the years, additional research suggested this number is approximately consistent across communities and time. So, suppose we randomly select 4 individuals to participate in this experiment. What is the probability that exactly one of them will refuse to administer the shock? So we're going to call these people Alan, Brittany, Caroline, and Damien. And so there are 4 scenarios in which exactly one person refuses to administer the shock, right? Remember that the probability of administering the shock is 0.65, which means the probability of not administering the shock is going to be 0.35. Right? This is a Bernoulli trial because there are 2 outcomes, a shock or a not shock. When we do 4 people, that's what makes it a binomial distribution. So 1 person is a Bernoulli trial, 4 people is a binomial. Right? So, scenario 1, Alan refuses, and Brittany, Caroline, and Damien all administer the shock. Right? Because the probability of refusing the shock was 0.35, and the probability of administering the shock was 0.65, if we multiply all of these probabilities together using our multiplication rule, the probability of this exact scenario is 0.0961. Also, we're assuming that these are independent, right? Alan, Brittany, Caroline, and Damien are strangers and have no connection to each other or any reason why these shocks, whether or not they administer the shock, would not be independent. So, scenario 1, Alan refuses and everybody else administers the shock. Scenario 2, Brittany refuses and everybody else administers the shock, right? And so Brittany, there's a 0.35 chance that Brittany refuses and a 0.65 chance for everybody else. and we multiply them together, and we get 0.0961 again, because multiplication is commutative, which means it doesn't matter what order we do it in. Scenario 3, Caroline refuses, and everybody else does it, which is, again, 0.0961. And scenario 4, Damien refuses, and everybody else does it, and that's the same probability again. So the probability of exactly one of these 4 people refusing to administer the shock is going to be the sum of all of these probabilities. All of these probabilities are the same, so we could just say 4 times, here, I'll just make that a times, 4 times 0.0961, which would be, carry the 2, 0.3844, if I just did that math right. So, the probability that exactly one person refuses to administer the shock is 4 times that individual probability. And there we go. Right? So, the question asks for the probability of a given number of successes k in a given number of trials n. In that case, k equals 1 success in n equals 4 trials. And we calculated it as the number of scenarios times the probability of a single scenario, because the probability for each scenario was the same, because they all involve the same number of successes and the same number of trials. It's just you multiply them in different orders, and the order doesn't matter with multiplication. For the number of scenarios, there is a less tedious way to figure this out, right? The number of ways that you can choose one person out of 4 is pretty easy. The number of ways that you can choose 6 people out of 20 is a lot more complicated, and we don't want to have to list out all of those combinations. Okay? So the probability of a single scenario is p to the k power times 1 minus p to the n minus k power, where p is the probability of success. So for the previous example, our probability of success, in this case, success equals not giving a shock, right? 1 out of 4 people don't give a shock. Not giving a shock is the success. So make sure you're paying attention to what's a success and what's a failure, otherwise you're going to get your numbers mixed up. Right? So 1 out of 4 don't give the shock. Not giving the shock is the success. So the probability of not giving the shock is 0.35. We have 1 person doing that. And then the probability of giving the shock was 0.65. And we have 3 people doing that. And if you look back on the previous slide, right, that's exactly what we see here. 0.35 times 0.65 to the third. Right? The binomial formula is the probability of the single scenario times the number of scenarios. And this is the probability of exactly k successes in independent Bernoulli trials with a probability of success p. Right? So earlier we wrote out all possible scenarios that fit the condition of 1 person refusing to administer the shock. If n is larger or k is different than 1, right? If we want exactly 2 people out of 9, it could be the first and the second, or the second and the third, or the third and the fourth, or the third and the sixth, or the 8th and the 9th. There's a lot of them. That's going to be a pain to do. So it's going to take a really long time, and we're likely to miss one. So instead, we use the choose function. choose function is useful for calculating the number of ways to choose k successes in n trials. Right? So n is your total, and k is your number of successes. So if we, for the previous example, we want to do 4 choose 1. All right, so your formula is n factorial over k factorial times n minus k factorial. Let's remind ourselves what factorial means. Factorial means that you multiply all the numbers, all the integers, less than or equal to that number, all the positive integers. So 5 factorial is 5 times 4 times 3 times 2 times 1. So for 4 choose 1, that's going to be 4 factorial over 1 factorial 4 minus 1 factorial, which is 4 factorial over 1 factorial 3 factorial, 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. And the wonderful thing about the choose function is that because everything's multiplied, you can cancel big chunks of your numerator and your denominator. And so in this case, the answer would just be 4. If we wanted to do 9 choose 2, it's going to be 9 factorial over 2 factorial times 7 factorial. So this is 9 times 8 times 7 times 6, blah, 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 all the way down to 1. And then 2 factorial is 2 times 1. And 7 factorial is 7 times 6 times blah, 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 all the way down to 1. And these 7, 6, blah, blah, blahs cancel out, and it's just 9 times 8 over 2, which is 72 over 2, which is 36. Okay? So which of the following is false? There are n ways of getting 1 success in n trials. Right? So n choose 1 is going to be n factorial over 1 factorial n minus 1 factorial. N factorial is n times n minus 1 factorial over n minus 1 factorial means the n minus 1 factorials cancel out, and that is equal to n. So that one's true. There's only one way of getting n successes in n trials. N over n choose n is 1, right? So how many ways can all 4 people press the shock button? Only one way. There's only one way to get everybody to do it. That's true. There's only one way of getting n failures in n trials. So how many ways can we get nobody to press the shock button? Also only one. So there are n minus 1 ways of getting n minus 1 successes in n trials, right? So n factorial over n minus 1 factorial n minus 1 factorial is just going to be 1 factorial. 1 factorial. And it's the same as this. Right? N minus 1 successes is the same as 1 failure, which is going to be the same as 1 success. So this is the one that's false. The binomial distribution, one of the key features of it is symmetric. So the number of ways of getting 1 success is the same as the number of ways of getting 1 failure. So when we put the two parts of the binomial formula together, there's the n choose k part, and then there's the p to the k times 1 minus p to the n minus k part, right? Where p is the probability of success, 1 minus p is therefore the probability of failure, n is the number of independent trials, and k, is the number of successes that we're looking for. So the probability of one success in 4 trials, right, is 4 choose 1. Probability of success being don't shock, 0.35 to the 1, 0.65 to the third. And we already said 4 choose 1 is 4, so 0.35 to the 1 times 0.65 to the third, and that gets us the probability that we already calculated, which I think was 0.3844. Which the following is not a condition that needs to be met for the binomial formula to be applicable. This one does. The trials must be independent, because if they're not independent, the probability changes, and you can't use the exponent, right? P to the k only works if all of the trials have the same probability p, which is also for number 5, right? We can't use the exponent if the probability of success is different. The number of trials n must be fixed because we use n in our formula. If we don't know what n is, we can't use the formula. Each trial outcome must be a success or a failure, because we only have 2 probabilities. The number of desired successes, k, must be greater than the number of trials. That's not possible. We can't have 8 successes if we only have 5 trials. That doesn't make any sense. A 2012 Gallup survey suggests that 26.2% of Americans are obese. Among a random sample of 10 Americans, what is the probability that exactly 8 are obese? Do you think it's pretty high or pretty low? It's pretty low, right? 26.2% is a little over a quarter, so 80% would be really unusual, right? So the probability that exactly 8 are obese, right, is going to be 10 choose 8, right? So 10 is our n, and 8 is our k. And 0.262 is the probability of success, where being obese counts as a success. Right? So 10 choose 8 times the probability of success, 0.262, to the number of successes, times 1 minus 0.262 to the number of failures. And it should be C. And you would then plug that into your calculator and it'll tell you what it is. And it is indeed pretty low, right? 0.05%. All right, we will do more practice with binomials because they're really important. Stay tuned.